Alright, let's talk about A to D conversion. And you have a series of homeworks to help you work on this, but let me talk you through the basic concepts first. And alright, my Zoom has disappeared. Somebody let me know. Oh, there we go. Okay, we're good. Alright, let me talk you through the basic concepts first, and then we'll look at this in the pick. So A to D conversion, right? We're mostly in a digital world in Engineering 250 and in 270, which means we think of everything as like one of two possible values, typically 1 or 0, high or low, true or false, on or off. But the actual world is more continuous than that, right? The voltage going into a pin is some number of volts, typically between 0 and 5 volts. But when you hook a wire up through a resistor to your power supply and you hook it up to a pin on your PIC chip, you're probably not getting exactly 5 volts. You might be getting something like, 4.963 volts. And the hardware inside the PIC looks at that and says, yeah, that's a logic 1. I'm going to take that as high or true. And if you connect this to ground, through one of our switches, you might actually get something like 0.11 volts. And the circuitry inside the PIC will say, yeah, that's a 0, that's a low, that's false. And when the PIC outputs a voltage, when it outputs, a logic 1 on a pin, it doesn't output exactly 5 volts. It might be 4.8, right? So in our living in an analog world, but thinking digitally, we have this notion of ranges of voltage, which look like that. And our understanding is that, anything from about here on up, we're going to treat that as a logic 1. And anything from typically, say, around this value on down, we're going to treat that as a logic 0. So if I can't produce exactly 5 volts, but I produce 4.9 volts, that's a logic 1. If I can't bring an input all the way down to 0 volts, but I get it down to, a quarter of a volt, that's a logic 0. But there's a region in the middle that's ambiguous. For example, if I put 2.5 volts into an input pin, should that be treated as logic 1 or 0? Well, it's really ambiguous. If you're putting in 2.5 volts, something is probably wrong. So this whole band in between here, we can think of as forbidden, or at least ambiguous. And so generally when we're building digital circuits, we don't want a voltage that's in this forbidden zone. We either want our voltages to be so close to 0 that we can say, yeah, that's a logic 0, or so close to 5 volts that we can say that's a logic 1. Alright, that's digital life. Analog is a different story. Analog, we can put in any voltage we want. 2.2 volts, not a problem, it's 2.2 volts. When you do a KVL problem in Engineering 120 and you get an answer of 1.6 volts, you don't say that's basically 0, right? No, you say 1.6 volts. So in an analog setting, right, any voltage is legal. And the voltage coming out of a speaker, a microphone, or the voltage going to a speaker, or things like that, these are not just binary. They vary in voltage level. So here's what we do. we can think of an input voltage range, and typically it'll be 0 to 5 volts because our PIC is powered with 0 and 5 volts. So anything in this range is imaginable. So what we're going to do is we're going to assign a number of binary values to each possible voltage. Because what are we doing up here? We're basically saying if your voltage is here, that's a logic 0. If your voltage is here, it's a logic 1. Well, there's a forbidden zone in the middle, but you know, in practice, probably it looks like this. If you put in less than 2.5 volts, we could say that's a logic 0. If you put in more than 2.5, we could say that's a logic 1. Right? That's one way to deal with an analog input. If we know our input's not going to necessarily be either down here or up here, but could be in the middle, let's just cut that input range in half and say anything below 2.5 volts, that's a 0. Anything above 2.5 volts, that's a 1. And if it's exactly 2.5, who knows? But nothing is ever exact. Alright, so this is a 1-bit analog to digital conversion. Taking an analog signal, I'm turning it into a digital value of exactly 1 bit. Not very precise, but you can do this, and it's actually used for a lot of things. Oh yeah, what if we did a 2-bit analog to digital conversion? Well, basically what I would do is I would take my input range from 0 to 5 volts and I would cut it into 4 bins. And I would say anything in this lowest bin, I'm going to call that 0, 0. This next bin will be 0, 1. Anything up here will be 1, 0, and anything that's really close to 5 volts will be 1, 1. So I'm using a pair of bits to represent an input voltage that could be anything from 0 to 5 volts, but this is a little more accurate. With a 1-bit analog to digital converter, if I get a digital value of 1, I could have 3 volts, I could have 5 volts, I could have 4 volts. They all show up as a value of 1. But if I use 2 bits and I get 3 volts coming in, my digital version is going to be 1, 0. If I get 5 volts, my digital version is going to be 1, 1. I can tell the difference between those 2 voltage levels. So we say it has higher resolution because we have 2 bits. Now I could do a 3-bit analog to digital converter. In 3 bits I can represent 8 different numbers. So I'm going to break my input range into 8 buckets. And I'm going to represent each of those with a 3-bit code as follows. So this is 2.5, this is 1.25, this is 0.625. This is 1.875. This is 5. I'm not going to do the upper ones. So 3-bit analog to digital conversion, I'm taking an input voltage somewhere between 0 and 5 volts and I'm representing it with a 3-bit number. And that 3-bit number tells me approximately what the voltage was. So if my 3-bit number is 0, 1, 0, I know my input voltage was somewhere between 1.25 and 1.875. If my 3-bit number is 111, my voltage might not have been 5 volts, but it was somewhere between whatever this value is and 5 volts. This is 4.375. So the more bits I use, the more accurately I can convert this analog voltage into a digital number and know from this digital number what my analog voltage was. Is this making sense?
Yep.
Cool. All right, this is how our computers interface with the rest of the world, right? This is how we take a signal from a guitar, and if we have a digital effects pedal, we turn it into a digital signal so we can modulate it, distort it, turn it into a feedback loop to add echo, do phase shifting, flangers, whatever, right? You have to take your input, which is analog, and turn it into a digital thing so that our microprocessors can chew on it and do things. And in the case of, an effects pedal, for example, at the other end of all of that, we need to go from this digital value back to an analog. So there's a digital to analog conversion process, DAC. We don't deal with that in here, and the PIC processor does not have a true digital to analog converter. But we can fake it. Guess how we fake it? By using pulse width modulation. Alright, but we're just going to talk about analog to digital. So what you should be realizing is that the more bits I use for my digital value, the more accuracy I have in my conversion. If I only have a single bit and I get a 1, I don't know if I got 2.5, 3, 4, 5, 3.7. All I know is I'm somewhere in this upper half of my voltage range. If I use 16 bits for my analog to digital conversion, I've got 65,000 buckets that I've broken this voltage range into. That's a lot of precision, it's a lot of accuracy. Right? If I look at my 16-bit value corresponding to a particular voltage, I can know that voltage pretty precisely, right? We're in the sub-millivolt range. So more bits, more accuracy, but it's also harder to convert into more bits. Single bit A to D, pretty simple circuit. 16-bit A to D, very complex. And there's a whole science to analog digital conversions. The more bits, either the slower the conversion process is, or the more hardware you need to do the conversion. And there's a trade-off there. And there's sampling theories. If you ever played with any of this stuff, you've probably encountered the Nyquist sampling theory, and that's a nice wormhole to go down. And that tells you how quickly do you need to sample something in order to be able to reproduce it, right? So if your input signal is changing over time, how quickly do you need to sample it? If it's just, a voltage level coming in and I sample it once a second, that might be fine. But if this is a waveform that's changing 8,000 times a second, I need to sample it more than 8,000 times a second, right? Because I want to catch all those little ups and downs. So let's look at what happens if we had a signal that was changing over time. And let's say this is a waveform that's coming in. And it's always somewhere between these two voltage levels. Well, if we do a 1-bit analog to digital conversion, what do we have? Over here, the signal will be considered a 0. Up here will be considered a 1 until you get to this point. Now it's a 0 until you get to here, and then it's a 1, and then when you get over here it's a 0, and then when you get over here it's a 1. Pretty crude, right? Now if I take the same waveform and I do 2-bit analog to digital, right, where this is 0, 0, 0, 1, 1, 0, 1, 1. So over here it's a 0, 1. Over here it's 1, 0. a brief period in here, it was 0, 1, and then it was 0, 0. And over here is 0, 1, and you get the idea, right? 1, 0, 1, 1, 1, 0, 0, 0, or 0, 1, 0, 0, right? So we get a closer representation of what this waveform looks like. And if we actually plot the waveform corresponding to this, well, 0, 1 sits right here, 1, 0 sits here, 0, 1 is here, 0, 0 is here, there's 0, 1, there's 1, 0, there's 1, 1, there's 1, 0, 0, 1, 0, 0, right? And we get this approximation of our waveform. It's not very good, but it's better than the 1-bit version. And if we use more bits, we can make this look more and more like our original waveform. That's the whole game we're playing with analog to digital conversion. We're trying to do something with a waveform that's moving probably smoothly in time, and we're trying to represent it digitally. Alright, that's the backstory. None of which you necessarily need to understand to do A to D conversion, but it doesn't mean anything to you if you don't understand what this is all about. But to actually do A to D conversion, it's just another subsystem inside the PIC processor. So let's go back and look at the data sheet. So okay, cool, good question. So somebody noted that in this example, the digital waveform is always below the analog waveform. But yeah, so I oversimplified this because, you know, presumably my voltage can go all the way up to here, right? So I would probably cut these things not right at these marks, but halfway through. So everything, you know, from here to here would be, say, a 1, 0, and so my digital waveform would be kind of right in the middle of that band, with, you know, half that subband above and half below. So this is just an oversimplification. But if you do this more neatly on a piece of paper and break those ranges up, yeah, you can have your digital waveform kind of in the middle. Yeah, you're welcome. So analog digital conversion, chapter 17. So the PIC has a built-in 10-bit analog to digital conversion module. Okay, 10 bits, that's 1024 possible values. So a 5-volt input range, we have a resolution of 5 millivolts. Right? Each bin from one digital value to the next corresponds to 5 thousandths of a volt, 5 millivolts. So that's a pretty good resolution, depending on what you're doing. If you want to have, you know, a variable resistor, a potentiometer, so you can have a digital volume knob, right? At one end it'll be 0 volts, at the other end it'll be 5 volts. Well, you would have 1,000 spaces in between, you know, off and on, that you could discriminate between. And you'd pick up each change of 5 millivolts in the input voltage. Alright, so using the A to D conversion system, a whole lot easier than describing what A to D conversion is about. First thing is a configuration register. We can choose what the high and low range are for this conversion. Typically, the high reference will be whatever the power supply is on the PIC, that's VDD. The low reference will be whatever ground is, VSS. So set these two bits to 0, which is the default, and with a 5-volt powered PIC, we'd be processing signals between 0 and 5 volts. But we can use external pins, something called external Vref plus or minus, to supply a high and low reference voltage. And you can supply just the high, just the low, or both. So that's what these two pins do. Alright, there's 7 input channels going into the A to D subsystem. There's 7 pins, AN0 through AN6. And those correspond to various pins. For example, AN0 is pin 1. AN1 is some other pin, oh, pin 2, right? AN2 is down here at pin 6. All the way up through AN6, which is pin 10. So we can choose one of 7 pins to feed into our A to D converter. That's what these 3 bits specify. Bit 0 enables the A to D subsystem. And then to do the conversion, you basically take pin bit 1, the go bit, and you set that high. And conversion takes a while, so you set this bit high. When the conversion is finished, this bit will be a 0. So you set it high to say start a conversion. When it finishes the conversion, the chip will set this bit to a low. So easiest way to do conversion, set this bit to a 1 and then just loop, keep testing this bit to see if it's a 0. When it's a 0, your conversion is done. And when you're done, your result will be in a pair of registers, AD result high and AD result low. So AD res H and AD res L, those together form a 16-bit register that contains your A to D value. And if your input voltage was 0, these will be zeros. If your input voltage was 5 volts, this will be the number 1023 in decimal. If you put in 2.5 volts, this would be 511 or 512. You can also set up interrupts. You can say interrupt enable for the AD subsystem, and when the conversion is finished, it will ask for an interrupt. You'll go to either 8 or 18 depending on the priority, and then you can check the AD interrupt flag to see if that's what got you to the interrupt. And if it did, then you can clear that flag and you can read the result registers and do whatever you want to do. So you don't have to sit around and wait for the A to D conversion to finish. You can say, go ahead and convert the input signal and let me know when you're done. And then you can go off and do other stuff, and when the conversion finishes, you'll get an interrupt, go off, process the input, and continue with your life. Okay, this third configuration register, ADCON2, we're not going to worry about. But this basically controls how the conversion takes place. So there's a question of how quickly do you want to do the conversion, and how long do you want to wait to read the input signal. And there's all of this in here that describes how to set those values up. And as soon as you start seeing things like temperature, you know you're in the wrong area. So yeah, there's all these great formulas like this with natural logarithms and temperature coefficients and all kinds of stuff. And we're not going to worry about that, right? And if you play around with this stuff in the simulator, all this stuff is ignored. But on practical hardware, right, if you're actually using a physical chip, you can go through this and come up with reasonable settings, and it's not too hard to trial and error. It basically do a fast clock, do a long acquisition time. But this is trying to find a sweet spot. Conversion takes time, right? If you try to convert too quickly, you get inaccuracies. But if you try to convert too slowly, you can't read that many samples per second, right? And if you're trying to process, music that's coming in, nominally up to say 10 kilohertz, you need to process that 20,000 times a second. That's the Nyquist sampling theorem. So 20,000 times a second, well, depending on your system clock, right, you may or may not be able to do that. So that's what all of these things are. The one bit that is interesting to us here is bit 7 of this register. That's the justification. Because Remember, we have the split in high, split in half, right, is another 16-bit register with a high part and a low part. Well, when you convert, you end up with a 10-bit answer. How should we put that 10-bit answer into a 16-bit register? Well, one possibility is to do it like that. A different possibility is to do it like that. So do we want to take our 10-bit answer and push it over here to the right or push it over to the left? And you can choose. If you say right justify, it'll go like that. If you say left justify, it'll go like that. And there's reasons for both. If you push it over here like this with zeros on the end, then it looks like a plain old 16-bit number. And if you're versed in dealing with 16-bit numbers, that's exactly what you want. But if you push it over here to the left so it occupies this part, you have the option of ignoring the low part and just taking this as an 8-bit value, pretending you have an 8-bit A to D converter and this is your 8-bit value. And that's easier and quicker to code. So that's what this does. Do you want the result to be left or right justified? Okay, one more configuration register, ADCON1, says do we want a particular pin to be digital or analog? This is the register we keep setting to 7F. We keep setting all of these bits to 1. What does 1 mean? Pin configured as a digital port. So if we want to use a pin for analog input, we have to set that bit to a 0. And when you set a bit to a 0, if I set this bit to 0, it says pin 3 can be used as an analog input. Okay, pin config 3 will be analog 3, and that would correspond to wherever AN3 is, this pin right here, pin 7. So we set this to 7F up to this point because we always want to do digital, but if we want to do analog input on one or more pins, we have to set the corresponding bits of ADCON1 to a 0, which is the default values. Alright, so that was 7 weeks in the making. There's the big reveal for what ADCON1 does. So hopefully that was worth the wait. Here's a cool picture of the A to D subsystem. So here's your 7 input channels. Based on your select register, your select bits, right, you choose exactly one of these channels to get routed through to this analog input. And it goes into the 10-bit converter. Here's the reference voltage, which can either come from the power supply or from these extra voltage reference pins, which are over here. So that configuration register controls the source for the analog voltage and the reference settings. And then here's a picture of what the actual analog converter looks like. So here's that analog input voltage coming in here. It gets loaded into a capacitor, or sorry, it gets loaded into a capacitor over here. So when you're acquiring the signal, that input signal, right, coming in on an analog pin, goes through this switch and charges up a capacitor. Capacitors, remember, will hold a charge. If I put 1.3 volts between here and here, and then I cut off the input voltage, this will hold that voltage for a little bit of time. And that voltage is what's sampled by the A to D converter to know what voltage to convert. So this is called a sample and hold circuit. And now we're into good electronic music stuff from the 70s. So sample and hold. And then the rest is detail. Alright, so let's take a quick look at those homework questions. Sketch a waveform that varies from 0 volts to 4 volts. Okay, make it an interesting waveform. Don't make it too bizarre, but you know, something other than just, you know, a simple sine wave maybe, or maybe a sine wave's fine. The voltage changes from 0 to 4, so the total range is 4 volts. Okay, figure out where half, 1.5, 2.5, and 3.5 volts are. Those are going to be our 4 voltage ranges that we want to use to discriminate a voltage level. Is it, you know, below a half? Is it between a half and 1.5? Between 1.5 and 2.5? Or 2.5 and 3.5? And assuming you want to represent a voltage as 2 bits, assign a 2-bit value to each of these ranges that you come up with. And now find a point on your waveform where it's about 3.6 volts and see what 2-bit value you would assign. Same for 3.9, 3.99, and 4. So this is you doing your own version of what I was doing here. Okay, and it's not very meaningful to watch somebody else do this. It really gets more meaningful when you do it yourself. So this is just kind of talking you through some of the stuff that I was doing. So whatever 2-bit value you assign for these, what are all the voltages that would get that 2-bit value? And then look at voltages close to 0. What 2-bit value would you assign to that? And what are all the voltages that would correspond to that 2-bit value? And then look at some things around 2.1, around 1.9. Okay, this is going from 0 volts to 4 volts. That makes it a little easier than 0 to 5. Alright, now suppose the waveform changes from 1 volt to 5 volts. So imagine, you know, our original waveform. Let's suppose this was 0 volts and this was 4 volts. Well, suppose instead I wanted to go from 1 volt to 5 volts. If I know that's the range of my input, 1 to 5, I can do my conversion exactly the same, except that this will correspond from 1 to 2, 2 to 3, 3 to 4, 4 to 5. If I wanted to analyze a signal and I knew that my input ranged from 172 volts to 176 volts, I would get exactly the same digitizing, because I would not assign bit values to 170 volts or 50 volts or 5,000 volts, right? I would say if my signal always goes from 172 to 176, well, this will be 172, 173, 174, 175. So what's important in doing this digitizing is not the value for the low voltage and the high voltage, but the range of voltage. In other words, the high minus the low. So that's what this next set of questions is asking you to think about, right? Suppose your waveform goes from 1 to 5 or minus 2 to 2. And then suppose it goes from 0 to 8. So I introduced the concept of resolution. That's basically how much of a voltage difference you can detect. In other words, what's the voltage difference, what's the voltage range for one bin, for one set of digital values. So that's the resolution. So now think of a voltage from 0 to 8 instead of 0 to 4, what happens to the resolution? 0 to 8,000, what happens to the resolution? Okay, all this was for 2 bits, now play around with 3 bits. 0 to 4 volts, what's the resolution? What if you do 4 bits, 5 bits, then try to generalize to n bits? And now, if the range changes from, say, 4 volts to 40 volts, and we're still using the same number of bits, what happens to the resolution? So if you do that, you can come up with a formula from the book for finding the resolution in terms of the high voltage range, the low voltage range, and the number of bits. Okay, but play with it, right? Dig around with your hands. This is how you get familiar with the stuff. Reading it in the book is not going to make it make sense. Okay, you've really got to explore this yourself, right? So get your hands dirty. And then this is just setting up the ADCON registers. So set up ADCON to convert from pin 3 using a standard voltage range, and with the result right justified. So look at the ADCON registers in the data sheet and figure out which values you need. And then if AN3 is 2.5 volts, what value would you expect in the result registers? Same thing for 1 1/4 or 3.75 volts. And then repeat those 3 questions, assuming that instead of right justifying, you left justify. Okay, and that's it for the A to D part of the homework. All right, questions? All right, on to the lab. So this is your last lab. It's lab 6, but it's actually listed as lab 7. This was going to be an optional lab, but I was talking to Izad, and he's going to do this for lab 6, and I think it's a good idea. So we're going to go ahead and do this for lab 6. Chapter 16 of the data sheet. This is an entirely new subsystem inside the PIC processor. This is related to serial communication. So suppose you want to hook a keyboard up to your PIC processor. Your keyboard sends out something like ASCII codes. ASCII is 7 or 8 bits of information. We don't want to send 7 or 8 bit values along 7 or 8 wires from your keyboard to the PIC. If you look at the wire coming out of a keyboard, it's a serial communication. It's USB. That's Universal Serial Bus, right? Serial. There's a pair of power lines and there's a pair of signal lines. It's a 4-pin protocol. This is old USB, not like USB 3 or C. So we basically have a single communication line that we're going to use to convey, say, 8 bits of information. And there's a really old standard for doing that, which is called RS-232. This was how the earliest dial-up computers communicated. This is how, bulletin boards and early chat rooms and things like that, how the machines that built those systems up talk to one another. And it's still a protocol that's effectively used inside this PIC processor. So here's the basic idea. Suppose you want to send the letter A. Okay, its ASCII code looks like this. It does not. It looks like this. Alright, 65 decimal 41 hex. That's the letter A. The letter B looks like this. And so on. Alright, we have one wire. Well, we have a ground connection between 2 devices, but we have one wire for sending information. So here's what we're going to do. We're going to have this wire be at 0 volts. And at some point, we're just going to set this wire high to send to 1 and low to send to 0. So if we want to send the letter A, we're going to make this high, and then low, and then low. Right? And that would correspond to the letter A. A 1, 0, 0, 0. Nope, I forgot to make it high. There's the letter A. And I started with the least significant bit first. If I wanted to send the letter, let's do C, because that's more interesting. If I wanted to send the letter C, I would go high for 2 and then go like that. So with a single line to convey a single bit of information, we modulate that bit value over time, and as long as the thing that we're sending it to knows how to count off the same amount of time, it can say, okay, there's a 1, a 0, 0, 0, 0, 1, 0, Oh, I just got the letter C. There's lots of details here. You need to know when you're starting to send something. You need to know when you're finished sending it. So there's start bits and stop bits and all kinds of other stuff. But this is the basic idea. We have one signal carrying a single bit, and we just modulate it high and low to convey a bunch of data. In this case, an 8-bit number, even though we can only send one bit at a time. Now, how would we do this on a microprocessor? Well, you can do it the same way you did your generation of a pulse width modulated signal in Lab 5. You set an output high, you wait a certain amount of time, you leave it high, you wait a certain amount of time, you set it low for 4 more intervals of time, and then you set it high, and then you set it low. So we can generate these waveforms ourselves by hand, right, by doing what we did in Lab 5. But there's a subsystem inside the PIC that will do this for us. And it's the Extended Universal Synchronous Asynchronous Receiver Transmitter subsystem, so the EU SART. Enhanced Addressable Universal Synchronous Asynchronous. So this can do lots of things. But it can generate these RS-232-like signals that we can use to convey information back and forth. And it's a pretty straightforward system to use. So there's a configuration register for doing transmission. And a lot of this we're not going to worry about because we're going to play with this in simulation in the lab. But this controls the clock that we're going to use, right? So we need to know how quickly to change this output value, right? Because the amount of time that corresponds to a 1 is critical. Because if this amount of time corresponds to a 1, then this is just a single bit 1. If this amount of time corresponds to a single bit, then I've sent a pair of 1s. Right, so this is what the baud rate is. When you have a serial device and you have to set the baud rate, that's controlling what this clock is. We don't have to worry about it, but we can choose how the clock's going to be generated. Are we going to do 8 bits or 9 bits? Bit 5, we have to set that to a 1 if we want to do transmission. We're probably going to go till about 2:30 today, by the way, because I want to actually take you through some of the code in the lab. The baud rate we're not going to worry about, but these bits down here let us control how quickly transmission happens. We're not going to have to deal with that. The receive control register, turn this bit on to say that we can receive data, right? So serial port enable, 8 or 9 bits, and we don't need to worry about the rest of these. And if certain error conditions occur, then you can get different kinds of errors, framing errors, overrun errors. These bits will be set to indicate that. So mostly we're going to ignore these other than just say enable transmission. And the sample code from the lab will take care of these for you. This is another register related to baud rate. We're not going to worry about that. In the data sheet, there's all kinds of formula used for adjusting the baud rate depending on the frequency of the processor and so on and so forth. We'll skip over that. But there's tons of tables and formulas that we don't have to worry about. So let's go down to the actual transmission. So basically when you want to send data, you load your character, your 8-bit value into the TX reg, transmission register. And when transmission is completed, you can have the system generate an interrupt. And when the interrupt is requested, you know that transmission is done and you can transmit another character. And to receive, after you've got everything set up, you basically read from the RC reg, right? And whenever a character is available, an interrupt will be requested. And so you can respond to that interrupt or just check the interrupt flag and know that you've got a character. Alright, so bottom line of all of that is basically once you set this thing up, you send out ASCII characters by just writing to the transmit register, and you read ASCII characters by reading from the receive register. Alright, so let's actually look at the lab. And so we've made some tweaks to this as of yesterday. So make sure you download the latest version of the lab. And this will click through from Canvas, but this is quicker than logging into Canvas. So Lab 7 online. Yeah, that was a fail. Alright. Alright, there's a lot of detail in this lab. The coding part is not the biggest challenge. The real biggest challenge is going through all of the steps and getting the MPLAB GUI to work with serial data for you. Okay. So objectives, you're going to apply basic serialization concepts, which are similar to what's used in most of the things that we do today, USB, Bluetooth, etc. And we're going to play with it inside MPLAB. Alright, so you can read the preamble here. But the punchline, you need to set up the subsystem to enable serial I/O, set up the baud rate, not too important for us. Set up interrupts if you want. We're not going to, I don't think I use interrupts in here. And then read or write to the transmit or receive registers. Alright, so you've got some sample code in here. This is a simple echo test. Okay, this will read from the serial port and then send a copy of what it reads back out to the serial port. So the main code just branches to main, the interrupt code branches to interrupt high. Main does serial setup, does an interrupt setup, and then it just sits here and loops. Alright, the serial setup, we set up the oscillator for 8 megahertz. We say we want digital I/O, so 7F into ADCON. We want to read from RB4, that's the receive pin, and we want to initially read from RB1, that's the transmit pin. And we set these up as inputs, but the subsystem will change them to outputs as needed. Okay, all of this stuff you can just take verbatim. Baud rate generation you can take verbatim, but if you do this on a physical PIC chip, this will set up 9600 baud communication. So if you take the output of the PIC chip and you run it into a serial port to USB converter, and then you run PuTTY on your laptop and you read from that serial port, you'll be able to read in your PuTTY window whatever the PIC chip is sending to you. And whatever you type in PuTTY will get sent to the PIC chip, and you can look at it in the W register. So this is interface, right? This is how we connect things to the outside world. Alright, interrupt setup is standard stuff. Enable interrupts, enable priority levels. Let's allow an interrupt on character reception. Enable high and low interrupts globally, and then we're done. Alright, so our main loop just says branch to loop. When we get an interrupt, we're going to come down here to interrupt high. Okay, we're going to get interrupted when a character arrives. And when a character arrives, you're going to basically wait until we're ready to transmit a character. And then we're going to take whatever's in the W register, which will be the character that we received, we're going to put that into the transmit register. And we're going to clear the interrupt flag. That's how we send a character. Okay, and this block till transmit ready basically looks at bit 4 of the transmit register, which will be set when we're okay to send a character out. Alright, so I'm going to run you through the first part of this, which is putting in that code and simulating the serial input and output process. And that's basically going to be experiment 1. Okay, but you're going to want to go through this yourself and make sure you can do it. And then you're going to change the code for experiments 2 and 3. Experiment 2, I want you to add 1 to each character before you send it back. And so if you send in the letters A, B, C to the serial port, you should get the letters B, C, D coming out. Okay, the code changes are trivial, because what does my main program do? I sit here in a loop and I just loop forever, but I get interrupted when a character arrives. So I move the receive register into W. At this point, the W register, that's a 0 by the way, at this point the W register contains the character I received. Well, if I increment W and I move that to transmit, that's experiment 2. So just throw an add LW1 between this and you got experiment 2. Okay, but don't just do that, right? Think about experiment 1 and make sense out of that. And then the third and final experiment is let's convert between uppercase and lowercase, and there's a set of rules here. If your input character is between 41 and 5A hex, add 20 hex to make it lowercase. If your input character is between 61 and 7A hex, it's already lowercase, subtract 20 to make it uppercase. So modify your code right after you read from the receive register into W, make these changes. I suggest making a function called, swap case that leaves you with the correct value in the W register, and then move that into the transmit register, and you should be good to go. Alright, so this is fun once you get it working, right? The real trick is getting it set up. So let's run through this. And I don't know if I have an MP Lab open already. I do. So I'm going to close this out. Alright, so I'm just going to take this code verbatim. Alright, that actually built. That's kind of amazing. Alright, so you got to do some things here, and this is tricky. So we've done the regular setup. We created finish, went into the project wizard, added the main file, and full path. Alright, we need to change some configuration options. So I'm going to go into the project. I'm going to right click and say set configuration customize. I'm going to go to simulator, under category select UART1IO, and then say enable UART1IO, and select window output. Alright, so I'm going to come in here, right click, set configuration, customize. I'm going to come down to simulator. I'm going to come to option categories and say UART1. I'm going to enable UART1, and if I don't have this option, you have to click the unlock button. Sometimes it's locked. So click that if you don't have these options. Say unlock, leave this at window, say apply, and say OK. Okay, that's all spelled out in here. And then go ahead and put your code in. Well, I already put my code in. Save your code. Assemble it, which I already did, and then we're going to simulate it. Okay, so let's put a breakpoint next to around line 39 where it says move WF transmit register. So around line 39, move WF, transmit register. So it's line 37 on my system. Alright, now we need to specify characters that we want to send into the serial port. So we're going to go to the stimulus tab, and this time we're going to say register injection. So come down here to stimulus, come over to register injection, and under the label put in whatever you want. You can call it serial, but under the register select RC Reg. So I'll just call this serial, and the register we want to inject to is the RC Reg, receive register. Alright, under the trigger select message, so change that to message. PC value and width you can leave as they are, and then under data file name enter data.txt. And then leave wrap at yes and leave format at PKT. Alright, so now you need to make a file containing the data that you want to inject into the serial subsystem. So find the directory that your project is contained in, which you were asked to note up top, but you can also find it here by just expanding this. So it's under your project directory, top level, data.txt. And make this with whatever your favorite editor is, but make sure it's plain text. So I'm just going to go with VI. And I'm going to say this is a test. Alright. You need to have quotation marks. Okay, well, okay, so it says put in a single line hello world. So I'll go ahead and follow the instructions explicitly. Okay, single line, make sure it has quotation marks in the beginning and end. Don't use WordPad, don't use, you know, Office or anything like that. You just want a plain text file. Okay, Notepad should work fine. I don't know what you use on Mac. Well, on Mac you can open the terminal window and do the same thing, but plain text file, hello world. Alright, now you're ready to build and simulate your project. Select debug project or assemble the code and start debugging. This may not work the first time. Okay. And there's something up here where it says after you do this setup you may need to close your project and restart it. But let's go for broke. So I'm going to rebuild my project. I'm going to start it running, and I'm going to go to my stimulus, and to fire the stimulus I'm going to hit this little play button right here. Okay, and guess what? My debugger just halted. I just jumped to this interrupt code, and I've just moved the receive register into W. Well, what did I put into my W register? I put a 48 hex. That's the letter T, an uppercase T. If I tell it to continue, now I've got a 65. That's a lowercase e. If I run again, that's a 6c. That's a lowercase l. Run again, it's another lowercase l. There's a 6f, that's a lowercase o. Run it again, there's a 20 hex, that's a space. There's W-O-R-L-D. There's an exclamation mark hex 21. And if I run again, it will repeat the process. It'll go back to the beginning of the file and read the next character, which is back to our uppercase H. So we're actually reading the contents of this file inside our PIC code. And the file is being used to supply the input. Alright, so that's step 2 of experiment 1. So you want to go through all of that, you want to document it, you want to note any problems, you want to make sure this works. Okay, the third step, and this is the slightly trickier one, is to simulate output. We can also have the PIC code generate serial output and have it appear in our simulator window. Okay, so what do we do? Look at the output tab and look for something that says UART1 output. If you don't see this tab, save your project, close, and reopen. So let's see if we've got this. So I'm going to go to my output tab down here, and I do not have a UART1 output window. So I'm going to close this project, and then I'm going to reopen it, and I'm going to run it a few times. So I see my W register changing up here. So now I'm going to go back to my output window, and now I have a UART1 output tab. So I'm going to click on that, and what I've got is an echo of what I was reading from the file. Right? So my interrupt code says, come down here when we've gotten the character coming in, wait until we're ready to transmit, read the character that came in, put it in the W register, and move that into the transmit register. So I've just made an echo out of my PIC. Whatever it reads from the file, it will send back out the serial port, and I'll see that data coming out here. So each time I hit that breakpoint, I'll see the next character from my input file, and it'll keep repeating. And if I change my input file, and I go ahead and run this, and look at our UART1 output. Oh, I need to stop my stimulus though. So click this again to stop the stimulus, and then hit it again to start. Alright, so there's the stimulus. Let's find our output. There's UART1. And our output is, this is the test, 1, 2, 3, ABC. Alright, so that's basically all the steps for experiment 1. Okay, and it's all spelled out in the lab write-up, but seeing it work will make it easier when you're trying to do this and it's misbehaving. Hopefully you'll believe that you can make it work, because you can, but it takes some fiddling sometimes. Alright, so that's experiment 1. Experiment 2, bump up the input before you send it back out, and ABC should come out as BCD. Experiment 3, do some more fancy if statements to convert between uppercase and lowercase. Put it all together in a report, all the usual boilerplate stuff. So so good screen captures for all of this would probably be just, this kind of thing after you've got it all said and done. For each experiment, go ahead and show this output, and then for caption the figures and show input is being echoed, or input is being incremented and then echoed, or input is being changed between upper and lowercase, and so on. Alright, questions about any of that? So we're skipping over what's listed as Lab 6 on ENGRCS.com, which was the A to D conversion. We're not going to have time for that. So we're just doing Lab 7, which is serial communication. So questions about this?
Nope, not for now.
All right, cool. All right, I will let you get to your labs. I'll hop in my office hours in a few minutes. Thursday, we will start talking about more software aspects. We'll talk about indirect file registers. This will be basically pointers and dereferencing pointers. And that'll move us into week 8. All right, cool. I will see you in lab.